Yes, sir.
Any specific doubts?
No, sir.
Have you read the full NCRT or these notes at least?
NCRT.
NCRT, the theory part, chapter 12.
Yes, sir.
Okay. What are these notes? It's basically from
Sir?
NCRT only. These notes. They are from NCRT only, this one. Okay.
Yes, sir.
Don't have time to read the book, you can read this one.
Okay, sir.
And if you don't understand this, you have to go back to the book. Okay. NCRT exercise, have you solved them? NCRT exercise.
Yes, sir. But not additional exercise.
Not?
Additional exercises.
That you can leave. After that, you can go to this learn CBSE.
Yes, sir.
So there you can solve the problems. So,
sir, question paper who is preparing, sir?
Question paper is from principal.
Okay, sir.
So, how was maths test?
Sir, நீங்க வருவீங்கன்னு எதிர்பார்த்தேன் சார் எக்ஸாம் ஹாலுக்கு.
For maths test,
Yes. Invigilator. It was tough, sir.
Okay. One thing they were saying is lengthy paper, not tough. So you can see the screen, right? Okay, I'll start slowly. So, atom, basically, you cannot see an atom. So you just have to assume atom is like this, or you can model the atom and then try to explain the experiment. And then further experiments will say there's some problem with the previous model, so you improve it. So J.J. Thomson model, what does atom look like? According to Thomson model, so according to J.J. Thomson, so the atom is like a positively charged uniform charge on which there are electrons embedded. Or I can put E minus for electrons. So and positive is uniformly distributed. So the thing that this can explain is emission of electrons from an atom. Electrons from an atom. So this model can explain. So who discovered electron? Any idea? Is Thomson only? Okay, I think it was cathode ray experiments. I think it was done by Crook. Okay. You have a tube like this in which you have anode and cathode, positive and negative plate, and here there is some gas, rarefied gas, because if it is too dense, it will become more complicated. And when you apply positive electric field, some charges will move towards the right. Electron will move towards the right, and the positive ions will move towards the electrons move towards the left, and positive ions move towards the right. So from that, the conclusion was there is something called a negatively charged particle present inside the atom. So to explain this, Thomson assumed that this atom will look like this, uniformly charged positive material in which the electrons are embedded. This is called plum pudding model or seeds in watermelon model. Okay, so this thing, after that, the next experiment which came was this Rutherford's experiment. Okay, here you pick a gold foil and bombard with the alpha particles. Okay, so if this picture of the atom was correct, the alpha particle is helium nucleus, which is 2 plus. Mass number is 4. So helium 2 plus is nothing but 2 protons, I think 2 neutrons. Without the electrons, 2 of them will be removed. So it's a positively charged particle. So if the atom was like this, if it goes and hits this atom, there will be some repulsion. Okay. But the experimentally observed fact was most of the alpha particles went straight through. Only few of them are getting deflected by a large angle, like this here, one here. Most of them are going straight. So if you draw this picture of the scattering angle of the alpha particle, which is positively charged particle, most of the alpha particles are getting deflected by a small angle. This angle is from 0 to 180 degrees. So 0 degrees means it's getting straight without any deflection. 180 means coming back. So 90 degrees means going this way or that way. Okay, so 90 degrees around here. So you can see most of the alpha particles are getting less deflected or no deflection. And only very few are getting deflected by a large angle, 180 degrees. So around 100, this is 10 to 7. So this cannot be explained by this model of atom. Because according to this model, if the alpha particle goes with positive, this thing, positive thing is uniform distributed everywhere. So it should, most of the things should get scattered by a large angle. So Rutherford modified this model of atom. So he concentrated most of the positive charge of the atom at the center, which is the nucleus. And the electrons are revolving at a distance. So with this model of atom, if you take an alpha particle and hit it, most of the thing will hit a place where there's no positive charge. So it will go through straight. So only few alpha particles which are going and hitting the nucleus, they'll get turned back. So here the scattering angle is 180 because straight would have gone like this, but it has come back like this. So scattering angle is here is almost 180 degrees. Here the scattering angle is 0. There is no deflection. Some of them will get deflected slightly like this, but if it gets close to the nucleus, it will get deflected like this. And if it gets still closer, you'll get deflected more. Still closer, you'll get deflected like this. Okay. So scattering angle will vary from theta equal to 0 degrees to 90 degrees here, and finally 180 degrees to the one which is coming back straight. So this graph shows most of the things are getting scattered at a lower angle, which is around 0 or 10 degrees or 20 degrees. So most of them are going too straight. Only very few are turning back. So this can be explained. This experimental fact can be explained only if I assume the atom model like this, where the positive charges consider a small region in the middle, and remaining parts are empty or few electrons are there. Okay, so this is Rutherford's model, and yeah. So with this thing, okay, the next thing is observed experimental fact is the emission spectrum. So in this atom, the positive charge is the nucleus in the center, and the electrons are here. Okay, so suppose there is only one electron in this atom, and suppose I excite this electron to a higher state by giving some energy. Okay, and then I remove this energy. So this will come back to this initial state, and in the process, it will emit a photon. Right, energy of the outer orbits is more compared to energy of the inner orbits. E1 is greater than, sorry, E2 is greater than E1. This we will study later. Actually, En is minus 13.6 by n square electron volts for hydrogen atom. So as n is increasing, the value of E is becoming less negative, and E infinity is 0. So the highest energy is 0. After that, it will become more and more negative. So the outer electron levels are high energy. So whenever the electron jumps from the outer orbit to the inner orbit, there is loss of energy, and that energy will come out as light or electromagnetic radiation in general, H nu. So the observed emission spectrum from these atoms, we just have to first knock this electron from inside to the outside some level, or the n equal to 2 or the next n equal to 3. Okay, and then leave it. So it'll jump back to the ground state. When it jumps back, it will emit radiation. So this is nu2, this is nu1. So obviously, nu2 will be greater than nu1 because the corresponding energy difference is more if we jump from third state to the first state compared to second state to the first state. So if we draw the emission spectrum as a function of frequency, you see this emitted frequencies only at discrete values. They are not continuous. So that means that this electron orbits, they are not at all the places. They can be only at specific values of radius. One can be here, it can be here. It cannot be anywhere. This is not possible. In between values are not possible. So this restriction is not being imposed by the Rutherford model. Rutherford model just only says the positive charge is constantly at the center and the electrons are revolving around it, but does not say electron can be only at this particular radius and there should be a gap and then some other radius and then there should be a gap. That thing does not Rutherford say. So Bohr came with this idea that all radius is not possible. So he imposed a postulate which states the angular momentum corresponding to that orbit, which is r cross p. Okay, where p is the linear momentum, m into v, and r is the radius, so which is mvr. It cannot take any arbitrary value, but it should be integer multiple of h by 2 pi, where h is Planck's constant. And n is integer, positive integer. So n will be like 1, 2, 3, so on, up to infinity. Okay, so so this puts a restriction on r because m is this mass of the electron and v is the velocity of the electron in the orbit, and n can have integer values. So if for n equal to 1, r will be some value, next will be n equal to 2. So r will jump to that value corresponding to n equal to 2. So in between, there won't be any values of r. And then we can use the force equation. The electron here, this is a positive charge, right? The simplest positive charge I can have is 1 proton. Okay, so the force, this is the hydrogen atom. So the force on this Coulomb force will be attractive force. That will be k into E square by the radius of this orbit, r square. Coulomb plus k into q1, q2 by r square. No, q1 is E plus E and q2 is minus E. So the force is this one. So this should be equal to mass into acceleration, centripetal acceleration, which is v square by r. Okay, so this is one relation, and this is second relation. So, and there are two variables, v and r. So I can eliminate v. Okay, so from this I can get v as something and put it here. So this will give me the radius of the first orbit because I'm considering first orbit. Okay, because I'll put n equal to 1 here. I'll put n equal to 1, that will correspond to my first orbit. Or in general, I can make it Rn. So just solving these two equations, I'll get this result. Okay, I'm going to put it here. See, these are the two equations. What is this quantization condition, which is given by Bohr? L equal to mvr, and this one, mvr equal to n into h by 2 pi. So mvr can about take arbitrary values. It can take values which are integral multiples of h by 2 pi. This is one equation. And the second one is the force. This one, the Coulomb force is equal to the mass and acceleration. 1 by 4 epsilon. This is the Coulomb force. between the electron and the single proton, because we are dealing with hydrogen atom. That's the simplest to deal with. That's equal to mass into acceleration, centripetal acceleration, v square by r. So this is one equation, 12.2. And the second equation is Bohr's quantization postulate. This one, 12.13. Okay, so if you solve this, there are two variables, v and r. So you can solve for r and also v. So solving for v, we get this one. This Rn means I have put n as n only. This n, I just keep it as n variable. So if I put n equal to 1, that will be the first orbit of the electron. Okay, so if you put r equal to 1, so I don't know, I won't not derive this one. This is simple. So you do it. If you don't understand, you can go through this derivation in this book. So this is the radius of, this is one of the formulas you have to remember. You can remember like this. And in this one, if you put n equal to 1, that is the first orbit. Okay, and this value, h is a constant, epsilon is constant, m is mass of the electron, e is charge of the electron. If you put all those values in SI units, I'll get this A naught as this one, 5.29 into 10 raised to minus 11 meters. So this was first, this is based on the Bohr's idea of quantization, right? So this is called Bohr radius, the radius of the electron orbit, first electron orbit of the hydrogen atom. Okay, so this formula you can remember. And then second one is the energy of the electron. You can also find V. So this is also simple derivation. And the energy of the electron is that there are only two forms of energy. One is the kinetic energy, half mv square, because electron is going a circular path around the nucleus. So kinetic energy will be there. Second is the potential energy between two charges, K into Q1, Q2 by R. Here one of the charges is negative, so we have a negative sign here. So Q1, Q2 by R, that Q1 and Q2 be E square divided by R. Okay, this is the total energy. So I think that they are derived earlier. One is kinetic half mv square. V expression has been derived, and this potential energy is Q1, Q2 by R. So one Q is proton, positive charge, other is the electron, negative charge. So that's why this negative sign is there. And R is the distance between the nucleus and the first electron orbit. So -1, this is half mv square. Expression for V is derived. Okay, so using that, I'll get the expression for energy as this one, total energy of the electron in the first orbit. Or I should say electron and proton together, because one interaction is the energy of the interaction, which is between the okay, you can also see energy of the electron. So one thing you should appreciate is the energy is negative. That comes because of the fact that the potential energy is negative. Potential energy can be negative depending on the appropriate reference I choose. Here the reference I choose is energy at the infinite distance, or the infinite orbit is 0. So here if I put r equal to infinity, I'll get u as 0. So with that reference, u becomes negative for other values of r. And this kinetic energy plus potential energy, kinetic energy is more dominant. Actually, it's twice. If you see, it's here it's 1 by 8. Potential energy is 1 by 4. So magnitude of the potential energy is more, but it's negative. So the total result will be negative, because potential energy is dominant and it's negative. So total energy will be negative. Another understanding of this negative energy is it means bound, because there is attraction between proton and the electron. So nucleus and the electron. So it's a bound system. So for a bound system, the energy will be negative. So this Bohr atom, Rutherford model could not explain these lines at only particular frequencies. These lines are at a particular frequencies because only the particular values of R are allowed. In between values of R are not allowed. So only those frequencies correspond to this particular difference of these allowed orbits. Only those will appear as lines. In between, there are no lines. Like jump from here to here will give me a frequency. Okay, but if there is a jump possible from here to here, that will give a different frequency, but that's not possible because there is no orbit here. There is no orbit. The next orbit is here, and the next orbit is here. So I can have frequency corresponding to this jump, or even this jump. But I cannot have frequency corresponding to jump from here to here because there is no orbit here. So only certain lines are possible. That's why in this spectrum, you see a line here and there's a gap. There is no emission in this for these frequencies, and there's a gap, and there is emission corresponding to this wavelength or frequency. So this can be explained only by Bohr's model, not Rutherford model, because Rutherford model does not put any constraint on the value of R. But Bohr's model put the quantization condition that R can be at only at particular values. So energy also we have found, and if I put n equal to 1, that will correspond to the energy of the ground state of the electron. That's n equal to 1. N equal to 2 is the first excited state. So this way I put the numbers, everything is constant. E is electron charge, m is mass of the electron, h is the Planck constant. And simplify it, you will get this energy formula. This is easy to remember, and this is for hydrogen atom, 20.6 by n square electron volts. And to convert to joules, I just have to put the value of E. So this, if I put the value of E as 1.6 into 10 to the minus 19, I'll get this in joules. So 1.6 is 13.6, approximately 21.8, and then 10 to the minus 19. So 110 will come, so it will become 10 to the minus 18. But this is an easy way to remember the formula. Negative sign indicates that the electron is bound. Bound in the sense like electron and proton will not fly away because there is attractive force between them, and they not fall inside because it's moving at a velocity. Like Earth is moving around the sun, but it's not falling into the sun, right? Because the centrifugal force, which is mv square by r, that's balancing this attractive gravitational force. Similarly, here the attractive Coulomb force is balanced by this centrifugal force because it's rotating around the nucleus electron. So the energy levels, yeah. So the energy level is minus 13.6 by n square. So if you put n equal to 1, it's minus 13.6. The next level will be n equal to 2, because that's a Bohr condition, right? N can be only positive integers, 1 and the next 2. It's a 1.5 is not possible, or 1.7 is not possible. So when you put n equal to 2, it will be minus 13.6 by 4, which is 3.4. So there's this much of gap in between. So next will be, if I put n equal to 3, this 13.6 divided by 9, so it's approximately minus 1.51. And next is n equal to 4. So one thing you have to realize is this gap is more. After the next gap is less. Next gap is less. So the E equal to 0 corresponds to very large level of value of n. So when the electron makes a jump from the outermost orbit, n equal to infinity to its ground state, the energy difference is maximum. So that will correspond to the maximum frequency of the photon. So the minimum frequency of the photon will be from the next n equal to 2 to n equal to 1. Next higher frequency to n equal to 3 to n equal to 1. If I impose the condition that the final state has to be n equal to 1. Yeah. So this is the ground state of the hydrogen atom. So if you make the electron to jump from n equal to 2 to 1 and n equal to 3 to 1, so any jump from n equal to 3 to 1 is higher energy difference. The energy difference between this and this is higher compared to energy difference between 2 and 1. So this transition will give a frequency, photon of frequency higher than this one. And the maximum frequency photon will come from this n equal to infinity, 0 to this one. So all these lines whose end state is n equal to 1 will correspond to one series called Lyman. Name of for scientist Lyman. So the second next possibility is the final state is n equal to 2. So for that jump should be from n equal to 3 to 2. This is the emission spectrum, right? So jump should be from higher energy level to lower energy level. If its jump is from 1 to 2, then I have to supply energy because I'm increasing the energy of this electron. So that will be absorption spectrum. So here I'm just considering the emission spectrum. So for emission to happen, the electron should lose energy. So it should jump from higher energy state to lower energy state. This is high energy state because it's minus 1.5. This is more negative, minus 13.6. And the highest energy is 0. So all the energies are negative, but the ground state is the maximum negative. So it's the lowest energy level state. Next is Bastian. Final state is n equal to 3, bracket. And the next one is P fund, where the final state is n equal to 5. Here n equal to 4. So we can have different series of lines. So that's what this line show. This one, alignment series. Okay, so this minimum wavelength, which corresponds to maximum frequency, is the jump from infinity to n equal to 1. And this is the minimum frequency or the maximum wavelength. This will correspond to jump from n equal to 2 to n equal to 1. Balmer series is next one. So this minimum energy corresponds to n equal to 3 to n equal to jump, n equal to 2 jump, because final state is n equal to 2. Similarly, fast chain is final state is n equal to 3. So this maximum billion that correspond to the minimum frequency, which corresponds to jump from n equal to 4 to n equal to 3. And this one is the maximum energy, minimum billion that will correspond to n equal to infinity to n equal to 3. Okay, so you can see there is a grouping. This is the Lyman series, this is Balmer series, this is Bastian series. This you can go through. For Lyman series, the final state is 1. Initial state can be 2, 3, 4, so on like that. Bastian's final state is n equal to 3, and jump can be from higher state. Only then there will be emission. Okay, so this quantization condition where L is L can have only force postulate, which says the angular momentum L, which is R cross P, which is MVR, should be integral multiples of h by 2 pi. And the chapter on dual nature of matter, photon has got energy E equal to h nu, and the momentum of the photon P is h nu by C. This you just accept it. This is the first time you encounter this is this chapter on dual nature of light. Okay, so from this I'll get this h by lambda, C by nu is lambda. Okay, so here I can h by lambda. Okay, MVR equal to so MV is the momentum, right? So momentum I can write as h by lambda into R equal to h by 2 pi. So h and h I can cancel. So lambda is 2 pi r by n. So what is 2 pi r? Electron is going around in a circular orbit of radius r. This is the nucleus. Okay, this radius is r. So 2 pi r is the circumference of this circle or the circular orbit. So n equal to 1 means the corresponding wavelength is 2 pi r. So I have to draw the picture correctly. One wavelength will fit in this entire circle. Suppose I take, let me take it n as 5. N equal to 5 means the corresponding wavelength, let me call it lambda suffix 5. So 5 wavelengths will split in this 2 pi r. So there will be like 1 wavelength, 2 wavelength. Okay, so 5 wavelength should, this is 1 wavelength. Okay, so 5 wavelengths will fit in this circumference of this orbit. Okay, so the Bohr condition, which is angular momentum of the electron, which is MVR, is integral multiple of nh by 2 pi. The other interpretation is only the integral multiples of wavelength will fit in this circumference. Circumference is 2 pi r, r is fixed, so 2 pi r is fixed. So all values of lambda are not possible. So lambda is also discretized. Lambda n. So lambda n is 2 pi r by n. If you put n equal to 1, that will be 1 lambda. If you put n equal to 2, it will give me second lambda. But in between the values of lambda are not possible. So this is another interpretation of the Bohr's postulate. That's why they showed here. This is 1, 2, 3, 4. Okay, here this is n equal to 4. So there are 4 wavelengths in this circumference. So this is the first wavelength, first one, second one, third one, fourth one. So this corresponds to n equal to 4. So this is another interpretation of the Bohr's postulate. Like electromagnetic radiation can have a dual nature says light can behave like a particle. Example is light whose energy is h nu and momentum is h nu by c. Usually momentum and all is associated with the mass, not with waves. But when we consider this wave, light or electromagnetic radiation as a particle, I can associate a wavelength, sorry, momentum whose value is h nu by c, which is h by lambda. Similarly, a particle, if I take a small particle, say electron, I can, because of dual nature, the particle can behave like a wave, and this corresponding wavelength of the wave is given as h by momentum of the electron. Okay, so here light, which is mostly a wave, can behave like a particle whose momentum is h nu by c. Similarly, electron, which we know as a particle, can behave like a wave whose wavelength is h by p. So here in this picture, I'm considering this is an electron moving around the circular orbit around the nucleus. But this electron I'm considering as a wave. When I consider as a wave, it has a wavelength lambda, and that lambda is such that integral multiples of lambda will fit in this circumference. Okay, so suppose this circumference is 4 meters, then lambda equal to lambda 4 will be 1 meter. Lambda 1 will be 4 meters, lambda 2 will be 2 meters. So lambda 1.5 meter is not possible. So lambda is quantized or discretized. So this is another interpretation of the Bohr's postulate. So with this, the theory part of the chapter is over. So as far as formulas are concerned, which you have to remember, meeting will get over in 4 minutes. You have to reconnect again, rejoin again.
Okay, sir.
So this formula list, this one. Okay, this go through NCERT. First formula I will say is Rn, radius of the orbit of the electron in hydrogen atom. Okay, I will remember this one. This is easy to remember. 1.53 angstrom units into n square. Radius is proportional to n square. And for hydrogen atom, it will be Z equal to 1 because there is only one proton. This same formula can be applied to hydrogen-like atoms. Hydrogen-like atom means I can increase the charge of the nucleus without with only single electron. So nucleus, instead of having single proton, I can have Z protons. And electron can be only single electron. If there are multiple electrons, it's complicated because there will be repulsive force between these two. But if there are multiple protons, it will not complicate it because proton are put it in small spaces within the nucleus. So the analysis will not get complicated. So whatever analysis possible to hydrogen atom, same thing and repeat for hydrogen-like atoms. Like multiple protons, Z protons and single electron. So these atoms are called hydrogenic atoms, I think so. Somewhere I put that. Hydrogenic atoms. They are like they have nucleus of Ze, but only single electron. If there are multiple electrons, simply complicated. Bohr model is not valid. Okay. Because when I put in the second proton, it's put in a very small space. It's as if it's put in with just 2 point charge. One with the charge of 2 protons or 2e and single electron minus e. But electrons it will be put in a different place. I cannot put it in the same place. Okay. So then the analysis will become complicated. It will be like a 3 charges. Got the idea? Okay. So the first formula to remember is this one. And by Z. So one way to remember is this, if n equal to 2 means obviously the radius is higher or radius is more, and it goes a square of it. Okay, and Z more means attractive force between the proton, the nucleus and the electron is more, so the radius will become shorter. So radius will go as 1 by Z. Z is the number of protons in the nucleus. If number of protons are increased means the force between the electron and the proton is more, so electron will come closer. So radius will decrease. So that way I can remember this 1 by Z variation. This for hydrogen atom. If I put Z here, it will for any hydrogen-like atoms. And energy formula, it's minus 13.6 by n square. Okay, and with Z, I think it goes as Z square. We input Z. The Z variation is not here. Okay, basically Z will come here. This is the Coulomb force, right? E into E. Instead of E into E, it will become ZE into E. So energy will increase as Z increases. Because the Coulomb force is, sorry, potential is Q1, Q2 by R, no? So Q1 is increasing Z times. So energy will go as Z times. So you can remember this one. And then if I can, this is in electron volts. So if I have to convert the energy to joules, I have to put the value of E as this one. And this is the Bohr quantization condition, angular momentum of the electron in the nth orbit. It's multiple of h by 2 pi. And when the electron jumps from the high energy state to low energy state, there will be a